Naming alkanes, aka the nomenclature of alkanes, if you want to go with the formal name. That'll be the topic of this lesson in my organic chemistry playlist. Now, this begins an entire chapter on alkanes, and the first half of this chapter will all be involved with naming alkanes. We'll name normal alkanes, and then complex substituents, and then bicyclic compounds as well. The latter half of the chapter will be dealing with the different three-dimensional conformations of alkanes. We'll have a lesson on constitutional isomers, one on what are called Newman projections, and then we'll finish it off with the conformations of cycloalkanes, the most important of which is the chair conformation of cyclohexane. Now, if you're new to the channel, my name is Chad. Welcome to Chad's Prep, where my goal is to make science both understandable and even enjoyable. Now, this is my brand new organic chemistry playlist. I'll be releasing these weekly throughout the 2020-21 school year. So if you don't want to miss one, subscribe to the channel, click the bell notifications. You'll be notified every time I post a new video. So naming alkanes. Now, you might recall a couple of chapters back, we learned a whole variety of different functional groups, and the alkane was just the first one. In fact, we often looked at it as kind of like the absence of all the other functional groups. So just a reminder, an alkane is a molecule that has all carbons and hydrogens, nothing else, and it doesn't have any carbon-carbon double bonds or any carbon-carbon triple bonds. Those would be alkenes and alkynes respectively, and we have just a slightly different set of rules, and we'll find out that all the different functional groups, whether it be alkenes, alkynes, alcohols, amines, ketones, aldehydes, so on and so forth, are going to have a little different spin on how we name those. And we're going to name them and learn how to name them throughout the year. But for now, we're going to focus just on the alkanes. And all the rules we learn how to name these here will still apply to all those other functional groups, just with a little extra rule here and there for those as well. All right, so it turns out we're going to talk about what's called the parent chain, and the parent chain is going to be the longest continuous carbon chain in a structure. So if we look at here, I've got a bond line structure, and recall that every vertex represents a carbon. So here we've got 1, 2, 3, 4, 5, 6, and then 7 or 7. So, and then an 8th carbon. So, and what I mean by continuous chain, then that's why I kind of skipped around a little bit at the end there, is that they've got to be directly bonded to each other in a kind of a linear chain. So 1, 2, 3, 4, 5, 6. And from here being 6, either I go up here to 7 or I go down to here to 7. But even though there's 8 total carbons in the structure, the longest continuous chain is going to be 7 carbons. And so if we kind of circle that longest continuous chain here, and I had the option of either circling this as part of the longest continuous chain or this one, and it is completely arbitrary. It wouldn't make a difference either way. So, but we're going to call that the parent chain. So, and then anything that's not part of the parent chain, so is going to be called a substituent. All right. So it turns out the number of carbons in the parent chain, or the number of carbons in a substituent, is going to be indicated by a certain prefix. Now, when it's the parent chain of an alkane, you use a suffix ane, but the prefix that comes before that is going to be a numerical prefix that describes the number. So if we take a look at, just a single carbon alkane as a parent chain, it's just simply CH4, and that's methane. So on the other hand, if we have a 2 carbon chain, so that's just ethane. And so meth means 1, eth means 2, and so on and so forth. There's a whole list on your handout there, and I'll put them up on the board here. So, but prop means 3, but means 4, pent, like a pentagon, means 5, hex, like a hexagon, means 6, hept means 7, oct, like an octagon, means 8, non means 9, dec, like a decade is 10 years, dec means 10, undec means 11, like un meaning 1 and dec meaning 10, and 10 plus 1 is 11. And then dodec, 2 plus 10, means 12. Now, some of you guys might not be responsible for 11 or 12, but most everybody is going to be on the hook for at least 1 through 10 here. So, and again, if you're the parent chain, we just add ane. And so again, 1 carbon chain is methane, a 2 carbon chain is ethane, propane with 3 carbons, butane with 4 carbons, pentane with 5 carbons, hexane with 6 carbons, heptane with 7 carbons, octane with 8 carbons, nonane with 9 carbons, decane with 10 carbons, undecane with 11 carbons, dodecane with 12 carbons. Now, obviously, real molecules get bigger than this, but you're only on the hook for up to 12 maximum for just about any class I've ever seen. So, cool. So that's for the parent chain. Now, the parent chain, again, always ends with that ane suffix for an alkane, but if you're a substituent, if you're a branch coming off the parent chain, we actually end it with a YL sound. And so in this case, this is just a single carbon right there, and so instead of calling it a methane group, we call it a methyl group. Let's draw that in red. So if you were a substituent with 2 carbons, it would be an ethyl group. 3 carbons, a propyl group. So 4 carbons, butyl, and then on to pentyl, hexyl, heptyl, octyl, nonyl, decyl, undecyl, dodecyl. So on and so forth. That's how that works. Now, again, students often struggle with these numbers from like 5 up for the most part. So because 5, pent, like a pentagon, and hex for a hexagon with 6, so on and so forth. But the first 4, and they're used a lot, are probably fairly new to you. So you got methyl, ethyl, propyl, butyl, and I like to say me, eat, peanut, butter. So to get that mnemonic down, to get those first 4 down. So methyl, ethyl, propyl, butyl, me, eat, peanut, butter. So if that helps, great. And if it doesn't, well, I'm sorry. You're going to remember that forever. I apologize. All right, so now we kind of know how to name parent chains with an A-N-E ending and the substituent with a Y-L ending. So let's kind of put this together on this fairly simplistic example. The way this works is we name the substituents first and the parent chain last when we name an alkane. All right, so we're going to say methyl first, and then in this case we've got 1, 2, 3, 4, 5, 6, 7 carbons in that longest chain, and recall that 7, the prefix is hept, and so we'll call it as a parent chain heptane. And so this is going to be called methyl heptane, but that's not good enough. And the reason it's not good enough is this methyl group could have been technically located just about anywhere on the chain. And so we now have to actually number that longest continuous chain, that parent chain. And you want to number it, in this case I could go left to right or right to left. And the way you choose is you want your substituent to have the lowest, what we call chain locator possible, where it's located on the parent chain, the lowest number possible. So notice if I go left to right, it'd be 1, 2, 3, 4, 5. It would be attached at the 6th carbon of the parent chain. But if I number this right to left, we can see that it would be actually attached at the 2nd carbon of the parent chain instead. And so that's how we're going to number this thing. And so before you name a substituent, you always give its chain locator first. And so instead of just saying methyl heptane, we're going to say 2-methyl. And then heptane. Now, one thing you should note, we always put a hyphen between a chain locator and the substituent, and we don't put a space or anything in between the substituents and the parent chain. Now in this example, we only had just one substituent, but a lot of examples we'll see we're going to actually have multiple substituents. And the key is there's no space, there's no hyphen in between the letters of the substituents and the beginning letters of the parent chain. It's just one big word. I like to joke with students that the goal in organic chemistry nomenclature is to make the longest word in the world, and we'll see that there are certain rules that will ensure that the word we use, the name we give to a compound, is as long as it possibly could be. All right, but this one's just simply 2-methyl heptane, but we can make this a little more challenging. So if we look at this one here, again, the first rule is to find the longest continuous chain. Now let's get this out of our way here. So longest continuous chain, and I can definitely see that this is going to be part of the longest continuous chain. So we'll go 1, 2, 3, 4, 5. And the question is, do I go over here or do I go up here? Well, in this case, it'd be 6, 7, or it would be like 6, 7 or 6, 7. But I have 3 different ways to get 7 carbons out of this. And so when there's a tie for how you can get the longest chain, they break the tie by saying, let's make the longest word in the world, is the way, again, I like to think of it, but they say break the tie by picking a way that has more substituents coming off the parent chain. So for example, if I just go 1, 2, 3, 4, 5, 6, 7, well then the only substituent would be this branch coming off the parent chain right there, just one. However, if instead of having numbered it that way, I go like 6, 7, well, now all of a sudden I'd have a branch coming off carbon 5 that's not part of the parent chain, and a branch coming off carbon 6 that's not part of the parent chain. I'd have 2 substituents, which is going to guarantee we get a longer word, and that's the way they break the tie. So, and in this case, I could have made this guy 7 as well. It actually is arbitrary in that case, because whether I have a 1 carbon substituent at 6 on the right-hand side or the left-hand side, I'm still going to get 2 substituents off this thing, and they're totally equivalent. So it didn't matter in that case. All right. So now we found our longest parent chain. Now that's not the actual way we're going to number this longest parent chain though, as we'll see. So first thing I'm going to do is I'm going to circle that longest continuous chain, that parent chain once again. So, and then I'll circle the substituents here as well. We've got 1 here and we've got 1 here. And so this will be the first time where we have more than one substituent, and there'll be another rule associated with how you name that. All right, but first I'm going to do is number that longest continuous chain again. And in this case, if I number this as number 1, this end, it'd go 1, 2, 3, 4, 5, 6, 7. And what we'd see is that my first substituent that I come across in the numbering system would be located with a chain locator of 5. But if I number it the other way and go 1, 2, 3, 4, 5, 6, 7, the first substituent I'll have will be located with chain locator 2, and the lower one is better, just like it was up here. And so you look for the first substituent you come across number-wise, and you want to get the lowest possible number. And so we'll number this starting with this end as number 1. So 1, 2, 3, 4, 5, 6, 7. All right, so here's where things get a little bit tricky. But if we take a look at this, this is still a 7-carbon chain. That's still going to be called heptane. At the very end of our name, the parent chain will be named heptane. But now we've got 2 substituents. We've got a single carbon substituent. That is still called a methyl group. But then I've got a 2-carbon substituent here, and that is called an ethyl group. Don't forget, me eat peanut butter. 1, 2, 3, 4. All right. Well, when you've got multiple different types of substituents, we actually name them in alphabetical order. So we don't actually name them based on where their chain locators are, it turns out. They decided the rule was going to be that you name them in alphabetical order, and ethyl comes before methyl in the alphabet, and so we'll name ethyl before methyl, and so this is going to be some form of ethyl, methyl, heptane. But again, before you ever say ethyl or methyl, you got to give me those chain locators first. And so ethyl's going to be first here, and it's located to the main chain, the parent chain, from carbon 3. And so we'll start this off by saying 3-ethyl. All right. From there, our next substituent is the methyl group, and it's located at carbon 2 of the parent chain. And so we'll say 2-methyl. Notice the use of hyphens here. So our chain locators are going to be surrounded by hyphens. So in every case, except when they're at the very beginning, I guess they'll just have a hyphen afterwards. But if they're in the middle of the word, those chain locators are going to be surrounded by hyphens. I like to say that we're going to separate numbers from letters with hyphens, is the way it usually works out. But it's really that chain locators need a hyphen around them unless they're at the beginning of the name. All right, so 2-ethyl, 3-methyl, and then we've just got left the parent chain. All the substituents are named at this point, and that's just simply, again, heptane. And again, no space here, no hyphen, just one big, long, ugly word. And again, we'd say this is 3-ethyl, 2-methyl heptane. All right, so we're making this more and more complicated as we go. So in this case, we've got to once again find the longest continuous chain. And students often struggle with this early on. And so one thing I recommend is look at your branch points, like this one right here. Look at those branch points and say, okay, in all the different directions, well, obviously going to the right is going to be part of this. But the question is, do I go up or do I go left? Well, here my longest chain going left would be 1, 2. My longest chain up would be either 1, 2 or 1, 2. And it's equal again, but I can see that I'll have more substituents if I go up, just like we did in the last example. So that'll be part of our longest continuous chain, and I'll circle that up until we get to the next branch point. And at this branch point here, I can go down and go 1, 2, or I can go off to the right here and go 1, 2, or 1, 2, or 1, 2. Those are all 3 equivalent, doesn't matter which one. But it's 2 carbons down, it's 2 carbons up to the right, and the tiebreaker again is going to be, does one of those get me more substituents that won't be part of the parent chain? Yeah, going off to the right will. And so in this case, so we'll go off to the right. And again, I could have circled either this carbon, this one, or this one. They would all be equivalent. It wouldn't make a difference. I just chose one at random. All right, but there's our longest continuous parent chain, and it is 1, 2, 3, 4, 5, 6, 7, 8 carbons long. And so the parent chain here is going to be named octane at the end of the name. But let's take a look at all those lovely substituents. We got 1 here, 1 here, 1 here, 1 here, and 1 here. And all of a sudden, this got a whole lot more fun. So if you look, this guy is a methyl group. These are both methyl groups. And then this guy right here is an ethyl group with 2 carbons, and this one is an ethyl group with 2 carbons as well. Now, when you've got multiples of the same substituent, you got to say how many of them you have. So using a numerical prefix. Now, not the same numerical prefixes that tell you how many carbons something has. But now we're going to have some lovely numerical prefixes like mono, di, tri, so on and so forth. And we don't use mono. When there's only one, you just leave that off. But the di, tri, tetra, penta, hexa, hepta, so on and so forth, we will use those. So in this case, like we've got 3 different methyl groups, so we're going to say trimethyl in the name. And we've got 2 different ethyl groups, so we're going to say diethyl in the name. Now what you have to know though is that when you alphabetize the different types of substituents here, you don't include that as part of the alphabet. You only alphabetize it either under ethyl versus methyl. And ethyl's still going to win, so we're going to name the ethyls first. But when we do, we'll say diethyl. But now we got to still number that longest chain. So if we number this from left to right, it would go 1, 2, 3, 4, 5, 6, 7, 8. But I'd see my first substituent would be chain location number 2. But if I go right to left, it'd be 1, 2, and one of my first substituents would also be located at number 2. It would be a tie. So then what do you do to break the tie? Well, then you go to the next substituent you come across. And so if I number this way, go 1, 2, and my next substituent would be this ethyl, which would be located at chain location number 3. And so if I go to the other side, then 1, 2, but here I've actually got 2 substituents that are attached at carbon 2. And so not only was the first substituent attached at carbon 2, so the second one would also have a chain locator of 2, and that's going to break the tie. Your second substituent's at 2, your second substituent from this direction would be located at 3 instead. This is the better way. We want to get those lower numbers for the substituents when possible. And so we'll number this one right to left. So we'll go 1, 2, 3, 4, 5, 6, 7, and 8. All right, so now that we got the chain locations for everything, so we're going to name the ethyls first, and I can see they are located at 3 and 6, so on the parent chain. So we're going to say 3,6-diethyl. All right, now if you look, when you've got multiple of the same substituent, between your chain locators, you're going to use a comma. So your chain locators get separated by a comma, but all your chain locators get separated by the actual substituents using hyphens. So keep that in mind. So I like to say that we separate numbers from numbers with a comma and numbers from letters with a hyphen, and that's usually sufficient most of the time. All right, so 3,6-diethyl, but then we've got 3 methyls, so we're going to say trimethyl, and 2 of them are located at chain locator 2, and 1 of them is located at chain locator 7. Now, the truth is, and a lot of students miss this early on, is if 2 of them are located in the same chain location, you do have to list it twice. And so this is going to be 2,2,7 trimethyl, and then finally our parent chain of octane. Now, a lot of students, when they start off, they forget one of the 2s, and they just say 2,7-trimethyl. And when I see 2,7-trimethyl, I'm like, well, one's at 2, one's at 7, and I don't know where the third one is. So you have to explicitly state all the chain locations. So if you're going to say trimethyl, you better have 3 chain locators out front of it, even if one of them is being repeated, to show that there are 2 of them attached there. So we have a couple more examples to go through here, and again, the key here is there's always special rules for certain situations that don't always come up, and I want to make sure we do at least one example of every special situation that you might come across, that you've really got these rules down pat. So, all right, so this top one here, again, first rule is find your longest continuous chain of carbon atoms, and so here, whether I start with either one of these carbons, it's the same length either way from this branch point, so I'll just choose this one here. And when I get to this branch point right here, I can definitely see I can get more carbons going off to the right than going up. So we'll go off to the right. And then from here, whether I go down or whether I go up to the right, it's the same distance either way. So it doesn't really matter which one you choose in this case. That's going to leave us with 3 substituents. And in this case, all 3 identical substituents, they are all methyl groups. All right. Now we got to figure out which way to number that longest chain. If we go left to right, the first substituent we'll come across would be at position 2. If we go right to left, the first substituent we'd come across would also be at position 2, and it's a tie. And just like in the last example, when there's a tie, well, then you go to the next substituent you encounter. And from left to right, that next substituent would be at 1, 2, 3, 4, would be at position 5. But if I go right to left, it would be at position 1, 2, 3, and that's going to be the superior method here of numbering this. So we'll number this right to left. 1, 2, 3, 4, 5, 6, and 7. And in this case, they're all methyl groups. So we'll just name them all at the same time. We'll say trimethyl for 3 identical methyl groups, and give, again, 3 chain locators to indicate where they're located. So 2, 3, and 6. So 2, 3, 6, trimethyl. And then the longest chain, 7 carbons, is heptane. And again, one big word. All right, so another example that'll iterate another special case we'll come across. So in this case, longest continuous chain from this branch point, definitely want to go off to the left here, not up. And then we'll go off to this branch point, and from here, whether I go up, it's 2 carbons long, and whether I go off to the right, it's 2 carbons long. It doesn't matter which one we choose. So, and a lot of people just like to choose right across the middle, but they get in the habit of going right across the middle and think they should always go right across the middle, so I'm just going to choose the other one this time. Just so you know, it doesn't have to be right across the middle, left to right, or right to left. So it is the longest continuous chain, whichever way you come up with that. Cool, and again, these have been equivalent. Either one would have worked. I just chose the other one so you can see that. All right, so if I number this left to right, the first substituent I'll come across would be at 1, 2, 3. But if I number it right to left, the first substituent I'll come across would be at 1, 2, 3. So there's our 2 substituents that are not part of the parent chain. So it's a tie. So then we move on to the second substituent. And if I number left to right, it goes 1, 2, 3, 4, and it would be low. The second one would be at 5. And if I number right to left, it would be at 1, 2, 3, 4, 5. And so whether I go right to left or left to right, it's 3 and 5 are where the substituents are located no matter what. And when you have a tie like this, well, if they're all identical substituents, great, doesn't matter. But if they're not, and these are not identical in this case, one's a methyl and one's an ethyl, well, you're going to use the alphabet to break the tie in that case. Not size, so we're going to choose the ethyl to have the lower number in this case, not because ethyl is bigger than methyl, but because it comes earlier in the alphabet. So a lot of students see us work this example and they're like, okay, so we're numbering this in such a way to get the ethyl the lower number to break the tie. And they think, oh, it's because of size. No, again, it's due to the alphabet. Ethyl comes before methyl in the alphabet. All right, so we go to name this. We're still going to name it in alphabetical order as well. So we're going to start off with the ethyl then, and we start off with 3-ethyl. And then 5-methyl. Cool, and then once again, our parent chain being 7 carbons long is once again heptane. And again, one big long word, no space. Cool, 3-ethyl, 5-methyl heptane. All right, so now we're going to move some examples of what we call cycloalkanes, and these are alkanes that form ring structures. And so when you've got that ring structure, so typically you're going to name the ring as the parent chain in most of the examples you're going to see. But we'll definitely work an example where the ring is actually not the parent chain, and we'll see what makes the difference and stuff like this. So, but in these 3 examples, we're going to name the ring as the parent chain. And when your ring has 6 carbons in it, like this one does right here, instead of calling it hexane, you put a cyclo prefix on it and you call it cyclohexane. Let's write that out over here. So one of the more common mistakes students make is when they're naming cycloalkanes is they forget to say cyclo at the beginning. So they just revert back to hexane like they would with a linear chain. So so keep in mind, get that cyclo prefix on there when you're naming the parent chain as a cyclo for a cycloalkane. All right, now the first example we're going to do here is going to have a single substituent. So, and this is the first time where I've actually included a halogen as a substituent. Now, you only ever name halogens as substituents. So, and you just simply, instead of saying like chlorine, bromine, iodine, fluorine, you put an O on the end for the INE. So it would be fluoro, chloro, bromo, iodo as a substituent. So just like you'd name a methyl, ethyl, propyl, butyl, pentyl, so on and so forth, you give the chain locator first, and then you're just going to say fluoro or chloro or bromo or iodo. So, and again, always named as a substituent, not as part of the parent chain. All right. Now, one other thing that's going to be a little strange about cycloalkanes is there's no end of the chain. Now, when we've numbered the longest chains in the past, we always started at one end or another end or something like this, and that's where carbon 1's going to be. But on a ring, there's no end, and so the key here is you get to choose, or at least have to figure out where carbon number 1 is going to be. Well, in the case where there's just a single substituent on your cycloalkane, we call this a monosubstituted cycloalkane, then your goal is to make sure that the substituent gets to be at the lowest possible number. Well, that happens if you make his location number 1. And so that's where it's always going to be. For a single substituent, wherever your substituent is, that's where number 1 has to be. And whether you go 1, 2, 3, 4, 5, 6 around clockwise or 1, 2, 3, 4, 5, 6 around counterclockwise, it's the same thing either way. Now, with only a single substituent then, because it has to by definition in how we number things be located with a chain locator of number 1, we actually leave the 1 out of the name. And so instead of saying 1-chlorocyclohexane, with just a single substituent, you just say chlorocyclohexane instead. And that's what we'll do here. And it's one big word. And again, if you say 1-chlorocyclohexane, it is technically wrong. So leave that 1 off. And again, a lot of students get confused here. So they're like, well, Chad, hey, so if I've got something like this, and I number my longest chain, 1, 2, 3, 4, 5, 6. And they say, Chad, so then this would just be chlorohexane, right? No, 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 no. This is 1-chlorohexane because when it's on a linear chain, that chlorine could be located attached to carbon 2 instead or attached to carbon 3 instead. And on a linear chain, you have to give me the chain locator because I don't know where it is otherwise. It's only on a ring with only one substituent that it has to be located at 1 by default. And notice it doesn't mean that the top's 1. I could have put the chlorine over here, and then we would have just defined that to be carbon 1 instead. So it's only for our cycloalkanes with one substituent that it's by default going to have to locate it at position 1. Not true for our linear system. So don't get that wrong. Common mistake students make at this stage. All right. Now, if you've got a di-substituted cyclohexane in this case, well, then your goal is to get the lowest possible numbers. But if you notice, you could number this, let's say, we'll put where the chlorine is at number 1, and that would put where the methyl group here is at number 2. And our substituents would be located at positions 1 and 2. But we could just as well have put the methyl group at number 1 and the chlorine at number 2. And so whether I number it this way, clockwise, or this way, counterclockwise, my two substituents are located at exactly the same numbers, the same chain locators, 1 and 2, either way. And so we have a tie. And if you recall, the tiebreaker is the alphabet. And so once again, this is our chloro substituent. This is our methyl substituent, and chloro comes first in the alphabet. And so we'll do it clockwise here with the chloro being at number 1 and the methyl being at number 2. So, and when you've got more than one substituent, now you'll include all your chain locators. It's only with just a single substituent that you'll leave out the chain locator because it has to be at 1. But here, you got to let me know where they're at. And so in this case, we'll name this still in alphabetical order. So we'll do 1-chloro and then the 2-methyl. So, and then again, big mistake students make is they'll just say hexane and forget that they need to say cyclohexane for the ring. Cool, so 1-chloro, 2-methyl, cyclohexane in this example. Now, students take what they've gleaned from a di-substituted cyclohexane, and then that often causes them to make a mistake when they get to a tri-substituted cyclohexane. And so in this case, they look and say, oh, let's see, we've got a chloro, we've got a methyl, and we've got a bromo for our substituents. Well, bromo comes first in the alphabet. We'll make him number 1. Well, again, we only ever revert to relying on the alphabet to break a tie. And we haven't verified that all the numbers are the same at all. And so notice we could, in fact, make bromo number 1. And when you do this, you always want to number in such a way, clockwise or counterclockwise, that you encounter the next substituent with a lower number possible. So notice, if I go around clockwise and he's 1, it'd be 2, 3, 4 for the next one. Whereas if I start with him as number 1, it would be 2, 3. And so we do it this way, and that would be 1, 3, and 4 for those chain locators. Well, notice, what if I start with the chlorine as number 1? If I start with him as number 1, I definitely want to go clockwise because then my next chain locator for where a substituent is located would be 2, and then 3, and then the bromo would be at 4. And so notice we'd be comparing 1, 3, and 4 to 1, 2, and 4. And in this case, there's no tie with all the numbers, and we don't have to revert to the alphabet at all. There's a tie at 1, but 2 is going to beat 3, and so that's out. Okay. Well, we had one other option for where we could put number one. Number one either had to be where one of these three substituents is located. So I guess the other one we could have tried is putting the one where the methyl group is located. And if we make him number one, then we're definitely going to want to go counterclockwise so that the next substituent we see would be located at 2. And then 3, 4, and the bromine would be located at 5 in this case instead. And so we can see our substituents would now be at 1, 2, and 5. And so for the first position, we definitely have a tie at 1. For the second substituent, we have a tie at 2. But for the third substituent, 4 is going to beat 5. And so the numbering system we've outlined in blue here is going to be the right one. So let's go back and take some of these off. But notice we did not have to revert to the alphabet. And that's a big mistake students make here, is they often revert to the alphabet on a trisubstitute like this before they've ever verified that the numbers are all the same. It's only when all the substituents have exactly the same chain locators that you then revert to the alphabet to break the tie. We never had a tie here. 1, 2, and 4 was going to be the best possible numbers we could have. All right, so now we've got the right numbering system, but when we go to name this, we still name our substituents in alphabetical order. And so not by number order. And so bromo is going to come first in the alphabet, then chloro, and then methyl. So that's another thing students screw up is they, we didn't use the alphabet to get the right numbers here, but then they forget that they need to name them in alphabetical order when they list the substituents. So, but that's what we need to do here. So we'll start off with 4-bromo, move on to 1-chloro, so then to 2-methyl, and then our parent chain again is cyclohexane. So once again, 4-bromo, 1-chloro, 2-methyl, cyclohexane. Now I alluded to the fact that we'd name one where the cyclo part of it was not the parent chain. So in the last examples it always was, but in this case it's not going to be the case because we have a straight chain here that is 6 carbons long, and our ring is only consisting of 4 carbons in this case. So, and the way it works is if you're, typically if one of them is longer or more complex with more substituents coming off, that's what you're going to make the parent chain. Well, in this case, if I name the straight chain as the parent chain, it's 6 carbons long with 1 substituent, the ring. If I name the ring as the parent chain, it's 4 carbons long with 1 substituent, the straight chain. And so I'll pick a longer parent chain in that case. Now, a lot of students make the mistake and they ask me the question, or they'll say, well, Chad, I can get a longer chain. I can go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and keep numbering through the ring. Well, the rules say you can't do that. So either your parent chain is the ring or it's not the ring. But you can't include the not ring and the ring combined in some sort of longer parent chain. It doesn't work. So in this case, it's just the not ring. And so our parent chain is this guy, and our substituent are those 4 carbons right there. Now our parent chain is 6 carbons long, so we'll call it hexane, and we'll number it in such a way that our substituent's located at the lowest possible number. So we're definitely going to number this right to left. Cool, and as you recall, so if this had just been a parent chain, we would call it cyclobutane. Bute means 4 carbons. But in this case, because it's a substituent, recall that when you do the parent chain, you have like methane, ethane, propane, butane, pentane. But if it's the substituent, it's methyl, ethyl, propyl, butyl, pentyl with a YL sound. And so this case, and again, instead of being cyclobutane, it's going to be a cyclobutyl group. And in this case, it's located at position 1. And so when we name this, we'll say 1-cyclobutyl. And then the parent chain is just straight up hexane. Now I know some of you are thinking, you're like, hey Chad, you got to give the 1. Oh, I do got to give the 1. It's only again when it's attached, when a substituent's attached, and it's the only substituent to a ring. Well, in this case, my parent chain is not even a ring. And again, I could have had 6 carbons, and I could have had this cyclobutane attached at carbon 2, or the cyclobutyl group, I really probably say. It could have been at carbon 1, 2 instead. And so if I don't say 1-cyclobutyl-hexane, if I just say cyclobutyl-hexane, well, then was it located at position 1 or position 2 or position 3? I don't know. It definitely has to be stated in this case. So when you have a single substituent, On a ring parent chain, that's when you don't include the 1. So, but again, in this case, we have a single substituent attached to carbon 1 of a straight chain. You definitely got to include the 1 in that case. Now, if you found this lesson helpful, please consider giving me a like and a share. Pretty much the best thing you can do to support the channel. And if you're looking for the study guides that go with these lessons, or if you're looking for practice problems on naming alkanes, so please check out my premium course on chadsprep.com.